Alrighty, pay attention. Pay attention out there. I need you to pay attention to this. This is one of the most important concepts that we have in this class, and it's one that gets messed up the most. So everyone listen closely. We're going to introduce a new function, a new complex function of position Z, which we call the line impedance function. And it's simply the ratio of the total voltage, a complex function of position Z, to the current, total current, a complex function of position Z. We take the ratio of those two things, and no surprise, we get a complex function of position Z. Now, here's the problem. Students oftentimes will tell me repeatedly throughout the entire semester that the ratio of the total voltage to the total current is the characteristic impedance, Z0, of the transmission line. And again, that could not be any more incorrect. It's wrong. It's very important that you understand the characteristic impedance is not the ratio of total voltage to total current. It's not even close to being that value. So first, let's look at it mathematically. Why is not the ratio of total voltage V to total current I equal to the characteristic impedance Z0? Well, we have our total voltage, which again is the sum of the plus wave voltage and the minus wave voltage. Each propagating wave propagating in the two opposite directions, each will create its own voltage, but what we measure is the sum of those two things, the superposition. This is very similar to kind of like we did in transimpedance parameters, where we determined the components of the voltage at port 3. But what we measure, what's physical, is the voltage at port 3, and so we have a voltage from one wire to the other wire at some location Z, and we can attribute that measurement to two different phenomena and have a component there of each. In the last presentation, we showed that we could write the total current that results in terms of the plus and minus wave voltage functions and a new value, which is the characteristic impedance. And so instead of having the original telegrapher equations solutions where we had I0 plus and I0 minus, we replaced them with a solution involving V0 plus and V0 minus and characteristic impedance. The important thing in all that is there was a minus sign that showed up where before we had a plus sign. And so if we go through and we take the ratio of the total voltage to the total current, and again, we're going to define that as a new function we call the line impedance function. If we insert these in here, we get this result. And we see that the only way that the line impedance function can be equal to the characteristic impedance is if all of this stuff right here is equal to 1. And generally speaking, V plus, the sum of V plus and V minus divided by the difference between V plus and V minus is not going to be equal to a value of 1. And therefore, the line impedance function is not going to be the characteristic impedance. This is the line impedance function written explicitly in terms of V0 plus and V0 minus for, again, a given value of beta and characteristic impedance. Yes, the line impedance function does depend on the characteristic impedance, but it depends on V0 plus and V0 minus and beta as well. Moreover, we look at the differences between characteristic impedance and line impedance function. Characteristic impedance is simply a constant that does not change either with position Z or with omega if it is lossless. The line impedance function is a function of both position Z and frequency omega. Characteristic impedance is purely real for a lossless transmission line. Line impedance function is complex. It will have both real and imaginary parts to it. So physically it's different and mathematically it's different. And because it's mathematically different, it tells us that it is indeed physically different. The ratio of the total voltage to the total current now is something called the line impedance function. This very complex relationship here, this function of omega n z, this complex function of omega n z, not this simple number, a constant, real valued, called characteristic impedance. All right, do not tell me that the line impedance function is equal to Z0. Don't tell me the ratio of total voltage to total current is equal to Z0. That could not be more incorrect. So the confusion, I think, comes back, and I get students that bring this up, there, I said, gee, V plus divided by I plus is equal to Z0, so I don't understand why the total voltage divided by the total current isn't equal to the characteristic impedance as well. But remember, this really defined what characteristic impedance is. Characteristic impedance is a characteristic of the transmission line. It's the characteristic that describes how that transmission line manifests voltage and current when there's electromagnetic wave propagating along. Again, if Z0 is higher, it essentially creates more voltage and less current for the same amount of electromagnetic wave power. If characteristic impedance is smaller, then it essentially manifests itself with more current and less voltage. So this is true and this is true. But once we start adding the things together, the numerator is the sum of total voltage. The total current is the sum of the numerator of each divided by the sum of the denominator of each. And there's no law of algebra that would conclude that somehow this would still be equal to Z0. So again, this is true and this is true. But then if I say the total voltage divided by total current, it is completely incorrect to say it's equal to Z0 or minus Z0. So we can show that everything we've said thus far is consistent in terms of our ratio of the total voltage to total current being the line impedance function, or the ratio of plus voltage to plus current being the characteristic impedance. And we can see that if we look at the line impedance function, again defined as the ratio of total voltage to total current, and it's written in this form, which clearly is not equal to Z0, unless, of course, all this big mess on the right is equal to 1. Well, if we look at this closer, there is we can see when this might possibly be equal to 1. We have V plus plus V minus in the numerator, V plus minus V minus in the denominator. It's pretty clear if V minus were happen to be 0, then we simply have V plus divided by V plus, it'd be equal to 1, and then that condition, the line impedance function, is going to be equal to Z0. If we only have a plus going wave, then the line impedance function is equal to Z0. But of course, this makes total sense, because if we only have the plus going wave, then the total voltage is just V plus, and the total current is just I plus. And of course, we know the ratio of V plus to I plus, which is the total voltage and total current if there is no minus wave, voltage and current. The ratio of V plus to I plus is equal to Z0. So if we take the line impedance function, when the minus wave voltage goes to 0, we can show in that condition that it is equal to V plus over I plus, which is equal to Z0. So again, it is consistent, both of the statements with respect to ratio of V plus to I plus, or the ratio of total voltage V to total current I. So one important point about the line impedance function, it depends on V0 plus and V0 minus, those two complex wave amplitudes. And what do those depend on? Remember, we said those complex wave amplitudes will depend on what we connect to the transmission line. Since the line impedance function depends on those two wave amplitudes, which depends on what we connect to it, we cannot say what the line impedance of a transmission line is in some invariant way. Characteristic impedance of a transmission line is the characteristic impedance of a transmission line. Whatever we connect to it, it won't change that characteristic impedance. Line impedance function, however, is a function that depends on the transmission line parameters, to be sure, Z0 and beta, but also depends on what we connect to the ends of the lines, which set up the values of V0 plus and V0 minus. Line impedance function really is a function that depends on our entire circuit, sort of like input impedance depends on the entire circuit. We can't say what the line impedance is until we know what is connected to our transmission line. By connecting something to our transmission line, then it will determine the line impedance function, and that line impedance function then will provide a constraint on the ratio between total voltage and total current. Just like any impedance doesn't determine what V is or determine what I is, but it will constrain the ratio of V to I. Once we have the line impedance function, when we attach something to our transmission line, then that will constrain the value of V and I that will will result. The ratio of those two must be, total V to total I must be equal to the line impedance function, which again will not be equal to the characteristic impedance, generally speaking.